welcome to our channel Euclid Mathematics. We have started lecture series on CSIR NET SET Gate and other competitive exam. Within that, I explained plenty of the videos on previous year question paper. If you wanted to check this video, you may check it all these videos from my playlist. Okay, now let's get started on today's lecture, which is completely based on CSIR NET previous year question paper, which is totally based here as a Lucas theorem. Okay, Lucas very important theorem from complex analysis, which is a Lucas theorem. So we have to apply the Lucas theorem over here in our example. Now let's get started on today's example. Let me read the question, then we'll move on solution. Here we have question from CSIR NET 4.75 marks question. So here we have question. Let's read the question. Let P be the polynomial in a one complex variable. P be the polynomial in one complex variable. Suppose all zeros of P are in upper half plane, and upper half plane it is given h is equal to z belongs to complex imaginary part of a z which is bigger than 0. Okay, imaginary part of a z bigger than 0 means upper half plane. Now here we can see this is the y-axis and this is the x-axis, this is the y-axis. So imaginary part of z bigger than 0, that means upper part it is coming, only upper part from our question. Okay, so imaginary part is bigger than 0, and then we have to prove, we have given 4 options. Okay, we have to prove that which one of the option is correct. Okay, now let's get started our today's solution. I'm gonna explain to you all first of all the theorem, which is very much important here, which is a Lucas theorem, and then we'll go for the options. So Lucas theorem, it says that, so if we have zeros of a polynomial, if a zeros of a polynomial which lies in upper half plane, only upper half plane, if a zeros of a polynomial which lies here in a upper half plane, then zeros of a derivatives of our polynomial which also lies here in upper half plane. Okay, this is the Lucas theorem. It says that Lucas theorem says that if zeros of polynomial which lies in upper half plane, then it's a derivative. Okay, zeros of, it's the derivatives of our polynomial which also lies here in only upper half plane. We do not go to down here, lower half plane or any other quadrant. Okay, it is completely goes to upper half plane. Okay, now here we have given P is a polynomial in one complex variable. One complex variable means, what is mean by one complex variable? Most of the students don't know how to create the polynomial which is having one constant variable, because in order to prove our options are wrong, that time we have to consider some counter type of the example. Okay, so for that we have to consider polynomial in one complex variable. Okay, that means we can see here z minus 2i, this is the one complex variable polynomial, or z minus zk, this one is a one complex variable polynomial. Okay, which include only one complex variable. It is easier, I hope you all can understand this one, so no need to explain it in detail. Okay, and we have given upper half plane quadrant, upper half plane is given, imaginary part of z is 0, bigger than 0, and similarly this example matches with the statement of a Lucas theorem. So Lucas theorem, it says that here, if all zeros of a polynomial pz lies in upper half plane, then zeros of a derivatives of pz, polynomial pz, also lies in a upper half plane. Okay, and now let's consider some counter example for our options. Okay, so I didn't shown here option till now, but once we understand first of all what we have given and what we have to consider our assumption, so then after we'll go for option. Okay, so first of all we have to consider the polynomial here. Okay, in our option we have given polynomial, operations on a polynomial, so that's why we have to consider a polynomial first. Okay, so here I consider p of z as a z minus 2i. Okay, so here we can see that p of z is equal to z minus 2i, which is a one complex variable polynomial, or you may select p of z is equal to z minus zk in general. Okay, and if you take polynomial differentiation of a polynomial p dash of a z, which is equal to 1. Okay, so in our option first, it says that option A, p dash of imaginary part of p dash of a z upon p of z bigger than 0 for all z belongs to real number. Okay, so for that find out the p dash of a z, then find out p of z. Earlier we found p dash of a z as a 1 and a p of z we taken z minus 2i. Okay, Now find out first of all p dash of z upon p of z. Okay, so here I found it here already. So p dash of z upon p of z, which is a 1 upon p dash of z, I got it 1, and p of z is a z minus 2i. Okay, so here z write z in the form of expanded x plus iy minus 2i. Okay, so what I have done, I just written z as a x plus iy because it is a complex number. Okay, always remember. So try to solve this quantity. Okay, because we want the imaginary part or real part of this quantity. So for that you cannot write directly imaginary or real part from this one. So first of all you have to rationalize our given term. Once you rationalize it, then you can easily identify which is the real part and which is the imaginary part. Okay, now see here, to go for the rationalization, only possible steps here to get it more into simplified form. 1 upon x plus iy minus 2i. Okay, so take I common from here, these two ones. Okay, so x plus I times y minus 2. Okay, go for rationalization. What do we do in a rationalization? We try to multiply the opposite sign of a denominator. Why we multiplying? Because a plus b into a minus b, we get the a square minus b square. That's why we want to remove this term from here. So you have to multiply opposite sign of a term here. So I did it here. If you are going to multiply at a denominator, do it similarly for numerator. Okay, because we want our original term remain same. So multiply it here, numerator to numerator, x minus I into I minus 2. So x plus y into x minus y, that means x square minus y square. That means x square plus I square is become minus it get plus x minus x plus y. What is the expansion? X plus y into x minus y. You need to know this expansion, which is x square minus y square. Okay, so like x square minus y square means I square is become minus 1, minus it getting plus 2 plus. Okay, and y minus 2 bracket square. Okay, so here we can see p dash of z upon p of z. Take the real part separately, the imaginary part separately. Real part we have here x upon x square plus y minus 2 bracket square plus I times plus I times imaginary part minus of y minus 2 upon x square plus y minus 2 bracket square. Okay, so I return our p dash of z upon p of z in the form of a real part plus imaginary part. So our first option, it says that imaginary part of our p dash z upon p of z, which is a bigger than 0. When it is bigger than 0? When we have all z which is from real number. Okay, any z you may select from real number for only imaginary part. Okay, now select here, this one is the only imaginary part. Okay, this one is the, we have to care about only this part. This one is the imaginary part. So when it is a bigger than 0, strictly bigger than 0, now consider where from we take here, we have imaginary part of a z minus y minus 2 upon x square plus y minus 2 bracket square. Okay, this is the imaginary part I consider here. So if I consider z from real number, okay, take such a element that can gives our value always bigger. Okay, so if z from real number, that means x plus iy. Okay, x plus iy, that means iy is 0. That means real z is from the real number. That means iy term, imaginary part is not there. So iy is 0. That means z we have only x. That means iy is 0 and y which is equal to 0. So I got the z as a x and y as a 0. Then imaginary part, which is a y bigger than 0. Now put y which is equal to 0. Now put y 0 in our imaginary part. Y 0 means minus it become plus 2 upon y 0 here, x square as it is, and y is a 0, minus 2 bracket square, it become 4. So we can see here 2 upon x square plus 4. 2 is always positive, x is always positive because it is having its square. Okay, so x square is always positive, 4 is always positive. So always we can see it is the bigger than 0. So if we consider our x z which is from real number, okay, that means imaginary part is 0 there. So our imaginary part which always bigger than 0, always bigger than 0. Okay, so it is quite easy, just little confusing to understand but quite easy to understand. Okay, so if you try to understand it 2 to 3 times, you can understand it very easily. Okay, now let's move for the another option. Okay, so I hope you all have understood my first option. Now next option, it is given real part of I times p dash of z upon p of z, which is smaller than 0 for every z belongs to R. Okay, now we want the real part. So here real part we have here, this one is the real part. Okay, so we have to care about this real part only. Now delete that imaginary part, we do not want it. Why? Because we want the real part, and multiply I to our real part only. And now check it whether it is smaller than 0 or not. Okay, similarly follow the procedure as I did earlier. Okay, so here I times imaginary p dash of z upon p of z, which is I times x upon x square plus y minus 2 bracket square. Okay, and I times I multiplied by I square, and I square and that negative it get positive. Okay, so positive y minus 2 upon x square plus y minus 2 bracket square. So I times I got the full term, I made it here. Okay, I got this full term here. So within that full term I want the real part only. So this one is the only real part. No, this one is the imaginary part. Okay, this one is the imaginary part and this one is the real part. Don't get confused, don't take real part from your directly p dash of z upon p of z, because I is multiplicand here. When you multiply I to our bracket, this p dash of z upon p of z, then whatever you get the real part, you have to select this one here. So real part here y minus 2 upon x square plus y minus 2 bracket square. Okay, so real part of our p dash of z upon p of z is y minus 2 upon x square plus y minus 2 bracket square. Okay, so we have here z from a real number. Okay, z from a real number, then obviously we can say that we write y as a 0. So if y is a 0 in our real part, that means real part of y is 0, y it is become 0, then negative 2 as it is, x square as it is, y is a 0, negative 2 square is a positive 4. Okay, now we can see it here, our real part of I for p dash of z upon p of z, it become negative 2 upon x square plus 4. So here this one is positive, this one is positive, but obviously we have negative term here. Okay, this one is a negative term, so that means whole term real part of p dash of z upon p of z, which is a smaller than 0, strictly smaller than 0 for z belongs to real number. Okay, if z is from real number, surely we can say that y term, okay, x plus iy, that y term is getting 0, because we do not have imaginary part in real number, that's why. Okay, so our option number B, which is correct. Okay, because we got the smaller than 0 value. Now let's move for option number C, imaginary part of p dash of z upon p of z, and which is bigger than 0 for z belongs to complex with imaginary part of a z smaller than 0. Okay, now here don't get confused. Now in this condition we have imaginary part of a p dash of a z upon p of z. Okay, we do not have I here. Okay, do not have I here, so we have directly p dash of z upon p of z. So here we can see p dash of z upon p of z, we want the imaginary part here, minus of y minus 2 upon x square plus y minus 2 bracket square. So you have to select directly from here. Okay, now go for the next steps. So here we can see our question here, that next condition, imaginary part it is bigger than 0. Okay, so minus of y minus 2 upon x plus y minus 2 bracket square, which is bigger than 0. Okay, so multiply negative under bracket, you will get the positive sign, or you take it downside. Okay, now we have one more conditions here. Okay, z we can take from any complex number, but imaginary part of z is smaller than 0, that means x plus iy, within that imaginary part is iy, which is smaller than 0, that means y is smaller than 0. So if y is smaller than 0, that means y is a negative. If y is a negative, then minus y plus 2, so minus y and y negative, that means y positive. Okay, y plus 2 upon x square minus y. Okay, y negative means minus y here, minus 2 bracket square, which is bigger than 0. Okay, this condition is very much important. Here we can see imaginary part y plus 2 upon x square plus minus y minus 2 bracket square. So this term is a positive, this term is a positive, y is also positive, because y we have taken negative here by using this condition, but after taking y negative I got the y positive. Okay, so y plus y positive, 2 positive, and this whole term is also positive. Okay, so that means whole this imaginary part is bigger than 0, that means our option number C, which is also true. Okay, so we have to take this imaginary part and then apply this condition, and after applying this condition you will get that imaginary part bigger than 0 for every z belongs to complex. Now our last option over here, so let's check out the last option. So imaginary part of p dash of z upon p of z, which is bigger than 0 with imaginary part bigger than 0, and z belongs to complex. Okay, now here we have taken already this term, but imaginary part we have taken there smaller than 0. So here we if we take bigger than 0, then we may see that y is a positive. So if y is a positive, that term is still remain negative. So it goes to smaller than 0. It is opposite option for option number 3. Okay, so in option number 3 we have given imaginary part smaller than 0, and this is a total converse part of option C. Okay, so if option C is correct, then option D is wrong. Okay, so it is only the converse part of option C because of we have this condition. Okay, I hope you all have understood my today's lecture. It is completely based on a Lucas theorem. Okay, so I hope nothing is difficult here. Even after, if you found anything difficult, let me know in a comment section. I will come up with some other videos. So thank you everyone. Thank you for my today's lecture.